Bueno, um, I think that we can start. Buenas tardes a todos. Bueno, como saben, esta va a ser una charla en inglés, entonces vamos a hacer todo en inglés. Good afternoon to everybody. Well, we're gonna start with the talk of today. Um, let me introduce you to Mohammed. It's a great honor for me to introduce our distinguished speaker, Dr. Mohammed. Dr. Mohammed holds a PhD in physics from Sharif University of Technology in Iran, which he earned in 2007. He further pursued his academic career with three postdoctoral fellowships at the University of Turin in Italy in 2010, the International School for Advanced Studies, CISA in Italy in 2012, and at the University of Sao Paulo, USP in Brazil in 2014. So currently he is an associate professor at the Fluminense Federal University in Brazil. His research interests include statistical mechanics, quantum field theory, and quantum information. And well, it's a great honor for us here in La Paz and for the Club of the Física Teórica in Bolivia to have you here, Mohammed. Thank you for accept the invitation. So I think that now we can start. The name of this talk is Fermionic Dualities. So, let's welcome Mohammed. So Mohammed, please, we can start.
Okay, thanks, Dario, for the introduction. And also thanks for Diego. Apparently, he was also sending me emails, and apparently one of the organizers. Well, it's a great pleasure to give this talk, especially for people from Bolivia, because when I visited Bolivia in 2014 and for a couple of weeks, so I'm kind of familiar with the country. And I always say to people that my trip to Bolivia in 2014 was one of the most exciting ones because I had the chance to visit so many interesting and authentic places. Some places that you can just find it in Bolivia, of course. I mean, well, sometimes I say this even for Bolivia because sometimes Eddie surprises me by not knowing some of these places that I actually visit. So it was a great really place. I really enjoyed it, and it's great now that after so many years, almost 11 years now, I have the chance to talk with people uh, in Bolivia. So what I'm going to talk is actually when I got this invitation to talk, I was told that this is going to be for undergraduate students, so I supposed to be a bit pedagogical. But then also they were telling me that it's a bit high energy field theory oriented, but somehow. Since probably you got a lot of talks specifically about high energy and probably cosmology, gravity, that kind of stuff. My talk is hopefully a bit going to be off that direction of the things, although the techniques and tools are more or less the same. So hopefully it will be a bit different. And hopefully it's not going to bother some of the people that they were waiting for that kind of stuff. So my assumption would be that I will start with really pedagogical stuff, and hopefully I will tell to also something that it would be useful for the experts. Anyway, so let's go ahead. So the outline is going to be introduction to quantum mechanics in qubits, and then I will speak a bit about why quantum mechanics is simple but also very difficult, and then I will tell you a bit about what we theoretical physicists normally do, and at the very end, I will start telling you what kind of problems we are trying to study these days. So why I say quantum mechanics is simple? Well, actually, because the mechanics is too simple. Actually, it's surprisingly too simple. So The reason is that probably you heard about the spins, right? Even in high school, and you know that with the spins you can understand the concept of qubits, which means that a qubit state can be described with two complex numbers like alpha and beta, right? Such that one is up and down. So when I write the 0 and 1, I mean they are the spins up and down. So the spin is angular momentum, but I will just drop out the h bar part, which is the unit that I don't care here. So when I speak about the spins, it will be spin up or down, and the spins are going to be 1/2 or -1/2, or something like that. You can even say it 1 and -1. Mathematically, it doesn't matter. Of course, experimentally, it matters, but for my discussion, it's irrelevant. So in principle, you can say that a qubit state is just as a simple vector like this, right? It's just a vector. And when you talk about the spin itself, normally we talk about, for example, a matrix. So we have an observable is normally just a matrix, right? And in this case, it's so simple because you have just two options. So the matrix that you have is just a 2 by 2. And then what happens is that in quantum mechanics, we say that the eigenvalues of this matrix are the possible measurement outcomes. These are the laws of quantum mechanics, right? So there you have the matrix, and the eigenvalues are going to be the possible measurement outcomes. And in this case, it's 1 or -1. As I was telling you here, I'm dropping off the h bar over 2. Then we have also the eigenvectors. So the eigenvectors are going to be the results of the measurements uh, after the collapse of the original quantum states. So this is another law of the quantum mechanics. And then there is an extra concept in quantum mechanics, and that's the probability. And what does that one says? It says that, for example, if the quantum state is something like this, alpha plus beta minus, if you remember, these are the eigenstates of this operator. So I'm writing the quantum state with respect to the eigenstate of this observable that I'm interested, right? And then the quantum mechanics tells us that the probabilities are going to be the absolute value of alpha power 2 and absolute value of beta power 2. And of course, the sum should be 1 because the sum of probabilities is 1. So the probability of measuring +1, which means spin up, is p plus 1. And the probability of measuring -1 is p minus 1. As simple as it is, right? So the quantum mechanics gives us these probabilities. For example, imagine that our state is, and I've written this state in the eigenstates of the SZ in this form. Then if I measure the spin in the SZ direction, then I'm going to get +1 with this probability, and I'm going to get -1 with this probability. This is amazing. If you think about it, I just told you all the laws of quantum mechanics in less than 2 minutes. And probably even if you tell these things to even a high school student who knows a bit of linear algebras, vectors and matrices, he can learn the rules, right? So it doesn't mean that you understand everything about it, because it's like, if you can give a kid of 5 years old a cell phone and says that, okay, play with it with the cell phone, and they can learn how to play it, but it doesn't mean that they know how the cell phone works, right? But anyway, they can play it, and you can play it. Undergraduate, high school student, not undergraduate, high school student who knows what are the vectors and matrices can play with the laws of quantum mechanics. Well, then what we have been doing in the last 100 years, right? It is so easy. What we have been doing. Well, the answer is in the complexity that emerges when we add more particles, right? So let's see what happens. So imagine that instead of 1 qubit, I have 2 qubits, right? Then the possible states and the SZ bases are plus minus, minus plus, and minus minus. So the so-called Hilbert space is going to be something like this, because now I have 4 options. and my vector is going to be 4 by 1. Okay, so the dimension of my vectors are now doubled. Okay, now let's go with the 3 qubits. Now for the 3 qubits, you can see that I'm gonna have more possibilities. Basically, I have 8 possibilities here. So my vector space is gonna be like this. So the vector that I'm gonna have is the general vector is gonna be 8 by 1, right? So again, it is double the previous case, right? So you can play this game with n qubits, and then you end up to see that the dimension of vectors that you have are 2 power n. Well, so obviously, whenever you have an exponential growth of something, there's a lot, right? So all of you guys, probably you are undergraduate students, you pretty know this. You are the generations of COVID, so you know what exponential growth means, right? So imagine that you have n equal 10, then this will be 2 power 10, more than 1,000 possible states. And if it's at 20 qubits, then you have more than 1,000,000 possible configurations. So this exponential explosion is a great challenge that we normally have. So this is the computational complexity that it has. We have in quantum mechanics. So the same problem appears also if you think to the observable, the matrices that you associated with the observables. Imagine like the 3 qubits, for example. Then, for example, the matrix that you associate for the observable, it will be 8 by 8 matrix. And if it's 20, it will be 1,000,000 by 1,000,000 size matrix. Nobody actually, and well, of course, you cannot do anything with pen and pencil, but probably this is the almost more or less the limit of the greatest supercomputers that we have. It's something like this. They can handle a matrix of this size. And if you think about it, it's pretty dramatic because we just have 20 qubits, right? So the matrix grows exponentially with the number of qubits. So then, in principle, you would say that this should be somehow hopeless, right, for a theoretical physicist. If you want to know everything about the system, then you need to take care of all this crazy matrices and Hamiltonians. But the truth is that in physics, we never try to know everything about the system. What we try is actually we try to understand. When we say that we understand something, we normally mean that we found the relevant quantities for the problem that we are studying. And then we try to calculate and measure those quantities. A typical example is the air in the room that you are sitting. Let's say that you're sitting in a room of 5 by 5 by 3. Then you can calculate that the number of approximately atoms that there are to 10 power 27, right? So, but do you care when you talk about the physics of the room that you are sitting? Do you care about the position and momentum of each atom? Well, that's basically impossible to talk about it because the number of atoms are so much. So what you do is that you find out what are the relevant quantities. Well, with a bit of thinking, you can see that probably the volume of the room that you are sitting, the pressure, the air pressure, and temperature are the most important quantities that you have in there. To say that you have an idea about the air in the room that you are sitting, right? So these are basically the relevant quantities. This has been an approach of the theoretical physicists from the time of let's say even Galileo, right? So you try you first of all forget about trying to understand everything about the system. You try to understand what are the most important quantities, and then you try to calculate and measure those quantities. And it is may sounds very simple, but it's not actually. In many cases, it's not. And in a physical problem, it's not easy to find what is the relevant quantity, what is the quantity which leads to a particular behavior in your quantum system. Anyway, so there are many examples that I don't want to bore you with all of these examples. I will just flash some of this stuff, right? For example, you can have Bose-Einstein condensation, and then you can see that the relevant quantity is a fraction of condensed particles. And then if you look at it carefully, you see that there is a matrix there that you need to find the largest eigenvalue of that matrix. So you see that from the calculation perspective, what you need to do is dealing with a matrix and the eigenvalues of that matrix. The same happens in superconductors. Here, you need to think about the energy gap and the supercurrents, and then you see that this energy gap is nothing except eigenvalues of particular Hamiltonian, and then the gap or the difference between the lowest eigenvalues in that system. So you need to do something with the matrices, right? There are many other examples that I can flash just here. As I told you, you don't need to know about this. My message is that for all of these quantities, the first thing that people did try to do was actually finding what is the important quantity for that, and then they try to calculate it. And there are many more examples that I will not bore you with those examples. And it's interestingly in most of the cases you see that you need to do something with their matrix, and maybe that shouldn't be surprising because as I was telling you, in quantum mechanics, observables are matrices, right? So probably you end up to do something like that. So if you're already familiar with quantum mechanics, you shouldn't be surprised about what I'm saying. Well, there are some other phenomena that, since I am interested myself on those things, I will flash a bit about those things too, like quantum phase transitions. So in the quantum phase transitions, the relevant quantity that we normally consider these days is entanglement entropy. And then what is entanglement entropy is nothing except this kind of sum over the eigenvalues of some density matrix. So you have a density matrix, and then you try to find the eigenvalue of that matrix. And as I was telling you, the density matrix size is going to explode exponentially. So it's not like this is a simple thing to calculate, even if you have, let's say, 20 particles or 30 particles or whatever. So you need to discover some ingenious methods to deal with this kind of stuff. Another example is the Shannon entropy, which pops out in the thermalization problems. And then in this case, it's actually diagonal elements of a matrix that you have, and then you need to do this sum over all these diagonal elements. And obviously, the sum is now again exponential, right? So these two examples are the stuff that I'm quite interested. So that's the reason I thought that maybe I can go through them in more detail. So we have, again, we try to find some relevant quantities for the problem that we have in hand and try to calculate them. So, I told you already that the quantum phase transition is, we have that kind of entanglement entropy as a relevant quantity, but I really didn't tell you what it is. What it is actually, imagine you have a system which is in this quantum system, which is in the zero temperature. And then there is a parameter you can change in the system such that the ground state behavior changes. This is really happening in even a very simple quantum mechanical systems, quantum many-body quantum systems. And then you see that there are some phase transitions. So the difference between quantum phase transition and the normal phase transition that you learn in your graduate courses is that normal phase transition is you change the temperature or magnetic field, right? So the temperature is normally the case. You change the temperature and you see what happens with that. With the system, a system shows, for example, goes from ferromagnet to paramagnet or something like that at some transition points. But in quantum phase transition, you have a zero temperature, and then so the system is in the ground state, and then you change one parameter in the system, and then you see that the nature of the ground state changes. Well, this has been in the interest of people, because we always like to understand the quantum phases, and the quantum phases, different quantum phases. And the interesting thing about the phase transition point is that around the phase transition point, we normally have some sort of a quantum field theory. The quantum field theory appears in this kind of problems when you are close to the quantum phase transition point. And at the critical point, normally we end up to have a conformal theory. As I said, I'm going to a bit more into to this stuff, because these are the things that I have done in my career. So I would like to know that what kind of piece I'm working on. So these are the kind of quantum field theory and conformal field theory appears in the quantum many body systems when you are close to the phase transition points, or you are at the phase transition points. Another interesting problem is the dynamics of the quantum system. So you have a system starts with the initial state, and then it evolves with the Schrodinger equation. And this is actually a much more difficult problem than even a quantum phase transition. And the reason is that here you have e power minus IHT acting on the state. So this already, the evolution operator is actually an exponential operator. And then it enters all the excited states, or everything about the Hamiltonian into the game, unlike the quantum phase transition, which normally just the lowest, the ground state and the lowest energy states they enter the game. Anyway, so in this systems, there are entanglement entropy, Shannon entropy, this kind of stuff are the quantities that these days people are interested. Of course, there are interest in these quantities also in people that they are purely interested in quantum field theory, and also people that they are interested in the black hole physics and stuff. So the methods that normally we use for this kind of problems are either we try to do exact calculations. In some cases, you can do exact calculations because the problem is exactly solvable. And in other words, we also say that, we have integrability in the system. And in these cases, you need to use some specific mathematical tools for the exactly solvability of the problems. People, they develop a lot of stuff in the last 60 years, and one can try to use it. Of course, in most of the, if you write some random Hamiltonian or system, normally these are not going to be exactly solvable. So these are really dots in the exactly solvable models are like dots in the space of all the problems that we have. Most of the problems are not going to be like this. And this shouldn't surprise you because, for example, there are few, even when you have one body problem in your graduate courses, you just have few, well, one body is normally exactly solvable, but you can already realize after having a quantum mechanics 1 and 2 in your undergraduate that there are just hydrogen atom and harmonic oscillators and a few other Hamiltonians that one can exactly solve. Most of the cases are probably you cannot do much except using some numerical or approximation methods. Anyway, so we also do this kind of stuff. You need to do some sort of smart truncations or matrix decompositions and all this kind of stuff. Okay. So one example that I would like to give you here, and the reason that I picked this is because this is something that the continuation of this work is something that we have been doing also with Eddie, and it's very connected to the essence of the title of the talk, is the Renyi entropy. Renyi entropy is a generalization of the Shannon entropy, and the calculations requires to calculate this entropy is actually the sum of powers of the principal minors of a matrix. And this is also something that that one can explain it even for a high school students if you already learned matrices and determinant in your high school. In my time, it used to be, we used to learn all these things in high school, but the time is changing, and then there are some other stuff that people they learn in the high school. But anyway, so what is the principal minor of a matrix? So you have a matrix, like let's say the 2 by 2. But if you remove the same rows and columns, like let's say you remove the row A1 and column 1, then it remains another, in this case, just a number, right? But if it was the matrix was bigger, then it would remain just another matrix. And then you just calculate the determinant of that guy, right? This is called principal minor. So the principal minor is basically determinant of submatrices of the matrix A. For example, in this 2 by 2 matrix, I have principal minor of order 0, which you remove both of the rows and columns, and you just consider that the determinant of this guy is 1. Now, if you take order 1, then determinant of the submatrices are going to be A and D. And if you don't remove anything, determinant will be AD minus BC. Simple, right? So these are the principal minors of 2 by 2 matrix. But if you take 3 by 3, then you will see that the number of principal minors that you have is actually 2 power 3. So you have 8 principal minors. So now imagine you are interested in calculating these principal minors power p, and then you want to do the sum over all of them, right? So this is a problem. I can even say it to the high school students. Take all the principal minors of the matrix A and then each one power p and sum them. Is it possible to calculate these things efficiently? Well, the truth is, and this is an example of this quantity that I'm saying. So this is just this one. I want you to calculate this for, let's say, size of 50. If your matrix is 50. So obviously we'll have 2 power 50 principal minors, right? So this sum will be 2 power 50 of them, and there is no a single supercomputer in the world that can actually calculate this efficiently. It's proven that this is the NP-hard problem. It's a very complicated problem, and the reason is the exponential number of principal minors that you have. So this exponential number is the problem. So, obviously, as I told you, why I'm bringing up this kind of problem, right? You may say this looks like a random, but if you remember, as I told you, if you want to calculate something like Renyi entropy, then for fermions, then you need to calculate something like this. So the calculation of entropy ends up to be this problem, which is a sharply hard problem, a very hard problem. But not that everything about matrix are difficult to calculate. Normally, eigenvalues and eigenvectors are much simpler. I mean, you can calculate them with a complexity of which grows polynomially. There is a determinant which you can calculate it with the Gaussian elimination with a polynomial growth of the complexity. So these are we consider this kind of problems easy. Trace is even easier, so it's ON. But then there are other problems like the one that I gave you, like sum of powers of principal minors, which is actually a very complicated problem. It's actually NP-hard problem. There's another version of another example is the permanent of a matrix. The permanent of a matrix pops out in the studies of the Bosonic systems. So if you guys are already familiar with a bit with the field theory, the Bosonic systems, they end up to take calculations of a permanent of a matrix. And what is the permanent of a matrix? Well, basically, permanent of a matrix is nothing except the same as determinant, but instead of those minuses that you have in the determinant, you put all of them plus. And then that's one of the biggest surprises. How come determinant with so many minuses here and there is easier than permanent, which doesn't have any minuses, right? That's a fun part of knowing about permanents. It's a very interesting things to understand, and but it's proven already, as I said. The permanent, which is exactly like a determinant without those minuses, is actually much harder quantity to calculate than the determinant. That's a very interesting fact. Anyway, so how do we calculate? Recently, we try to study these things with the following methods, which might be in the interest of those that they know a bit of quantum field theory. So what we do is we first try to find a representation of this kind of problems with respect to something we call Bayesian-Grassmann integrals. So this is like a field theory language, right? Those that they are familiar with the fermionic field theories, they know this kind of path integral kind of integrals. What it is? Well, it has, it looks like a scary thing, but it's actually very simple. So Bayesian-Grassmann integration is actually based on a kind of fermionic variables that they have this kind of anti-commutative behavior. So if you have theta I, theta j is equal to minus theta j, theta I. So this is a funny behavior. So if it was a simple integration, theta I, theta j would be equal to theta j, theta I, right? But in this case, it's minus. And then the integration properties are just integration over d theta is equal 0 and integration over theta d theta is 1. And this is amazing. This has amazing consequences. As simple as it is, it has amazing consequences. So one of the consequences is that you can write those quantities that I told you as this kind of integrations. The quantities like determinant, permanent, and many others that I may flash for you guys in a few minutes. They can be written as some sort of, some people, they like to call it fermionic integrals. I prefer to call it Bayesian-Grassmann integrals, right? And they help us to manipulate these quantities in a way that ultimately we can have a good estimations of those quantities. So, and what are those manipulations? The most important one is probably using some sort of fermionic dualities that we have been developing. And using these dualities, one can have another version of fermionic integrals for those quantities. And then after having this new version of fermionic integrations, we map them to some sort of normal Boschonic integrals. When I say Boschonic integrals, I mean normal integrals that you are familiar from your undergraduate studies, and then we try to approximate those guys. So if I put it in a chart here, so what I told you is actually I have a hard, and then well, what does it mean hard problem? As I told you, hard problems are those problems that they are exponential. Exponential in the sense that you need exponential time to calculate them. So you have this hard problem. You write a fermionic representation for these hard problems. Then you use fermionic dualities and find a dual fermionic representation for these problems. And after that, you Bosolonize the representations. And with Bosonization, I mean you write a version of this integrals that is just a normal integration, and then you use what I call steepest descent or some approximations that we have. For the sum of powers of principal minors, I told you, which is actually, as I told you, NP hard problem. And we have good results. And then in the last year and a half with Eddie, we are now trying to apply this to many other hard problems. And Eddie has been working days and nights to classify problems. And this is something that he prepared just yesterday or maybe this morning. I don't know. I put this just this morning. So this is a classification part of the classification of the hard problems. And these are, at this moment, they look mathematical. So, and I'm not going to go into this problem. So this is the hardest problem we have. And then you can have many quantities that they are familiar for people that they do either mathematics, combinatorial, or field theory, or many body systems, right? So the problems, they get easier, and also from the left to right, the problems get easier, such that the Fatian and determinants are the polynomial. Everything else here is actually a hard problem, including the Haas. So each one of these problems that we have here, there are physical problems associated with them. For example, in the case of the sum of powers of principal minus, I told you one example, which was the calculation of the Rayleigh entropy of fermionic systems. But it also, you can show that even something like Hubbard model is the same. There are many other problems in statistical mechanics and also in high energy physics. With high energy, I mean, mostly I mean the fermionic field theories that you can map to one of these guys. This is actually quite impressive because it's inside this stomach and everything starts coming. Actually, applying this program to bunch of physical problems that they are special cases of these mathematical problems. Okay, I hope that the program is clear, the purpose of the program, but I told you a bit. Sometimes it's more general and easier to grasp. So what we are doing is basically exploring, first of all, classifying these problems, trying to explore five quantum systems and their emergent problems. We have much restrictions. We are not like we are just concentrating necessarily, well, whatever problems that we'll be interested in calculating it. So if the problem might be a problem, it can be a combinatorial problem, it can be a field theory, high energy problem, whatever it is, right? Because it's kind of general. And then, of course, we need to develop tools. These are things that we have ideas how to do them, but this is something that we also. And as I said, this will be something which is interdisciplinary because this formalism is useful in different part of this. So obviously, as I told you, I hope that you are convinced that quantum mechanics is actually a very, very simple theory. It's very simple. Emerges when you Hilbert space and all these things. And then many properties that fascinate us in quantum mechanics unravel, they come out as the emergent particles. So if you are interested to this kind of problems, complex physical systems, or some advanced mathematical tools that can be useful in different branches, happy if you guys to join us here. Already me here for a while, and I've been very happy with him. So hopefully, if you go come here, we'll have a good group of also Bolivians here. So with this, I will actually I have some times, but I think I explained the things pretty fast, so we'll have a lot of time for the questions. If now available for your questions.
Ok, thank you very much, Mohammad. Bueno, para todos, si hay preguntas, pueden hacerlas si quieren en inglés o si quieren, las pueden poner en español y las pueden encender el micrófono o en chat. Well, if there are questions, please, well, you can write them on the chat or you can. Well, there's a question here. Okay. With Eddie, we studied the fermion chain. Are other graphs with exact solutions as complete graph?
Well, all these techniques that I'm telling you are actually general, right? If the idea is about a combinatorial problem, that combinatorial problem is defined on a graph and it has a fermionic representation, then this kind of techniques should be applied. Problems that when you put on the graphs, they are exactly solved. For example, you have an Ising model, let's say, and then you can solve this Ising model, let's say, classically. Not necessarily just for the quantum system, it can be a classical system too. Let's say that you have a bunch of spins, classical spins of up and down, and then you want to know what is the partition function of the system for this one. Depending on the graph that you put, sometimes there are techniques that you can calculate the partition function or the free energy of the system with those techniques. Exactly. Most of the time, it's not possible, but sometimes it's possible. A very famous example is the Ising model, the classical Ising model, which you have a bunch of spins up and down, and then the Hamiltonian is just multiplication of S with the other S. Normally, this is defined as the nearest neighbor interaction, and the nearest neighbor interaction in 1 and 2 dimension is exactly solvable. Now, if it goes to 3 dimensions, it's impossible. And then if you put on a graph, which everybody is in interaction, they are coupled with each other, then again, it's exactly solvable. So it really depends on the problem and when it is exactly solvable and when it's not exactly solvable. It is in some cases, depending on the model that you have in your mind. In some cases, it is the classification is clear. With the classification, I mean when it's solvable and when it's not solvable. And for some other cases, models is not necessarily. Ising model is a prime example. The classical Ising model is a prime example that has been studied for the last almost 100 years. And more or less, with that, more or less, we know when it is exactly solvable and when it's not exactly solvable. And this is also mathematically really related to what I'm saying, because you can show that in some cases the partition function or free energy leads to some determinant that you need to calculate. And when you get the determinant form of the free energy, for example, or the Faffian form of the free energy, you say that it's exactly solvable, so it's done. So you are happy. But these are when you have graphs that they are special graphs. They are not like most generic ones. Most of the time, we don't have a well-known non-trivial statistical model which is exactly solvable on any graphs. Most probably we don't have it. So I don't know that this answers the question, or the question meant something else.
No, yes,
I don't know
okay.
who was there.
I was wondering about the complete graph specifically. It is known?
What is known? I couldn't get it.
the complete graph with quartic interactions, and if it's not,
Yes.
how to compute the correlations.
Yeah. So, if I understand correctly, if with complete graph you mean that everybody is coupled with everybody else with the four
Yes.
fermionic ones, you can actually calculate the partition function exactly in this case with the technique which we call it a bosonization. Some people they call it Hubbard-Stratonovich. So you can do this and make it actually exactly solvable. This is supposed to be a simple problem actually because everybody's coupled to everybody else.
Thank you.
Was this your question?
Yes, thank you.
Yeah. No. You're welcome.
Thank you. Maybe if there are other questions, please you can write it on the chat or you can use your microphone. Well, I have a question. In this, when we use, for example, these fermionic dualities or these kind of representations, are there some energy losses? Maybe I don't know if there's a loss of energy, not of energy, of information. Sorry, if there's a lot of information about a system, and I would like to know if, in that case, how we can treat that loss of information when we use this kind of tools.
Okay, so you see, I started the idea by saying that in any system, basically, as a theoretical physicist, we try to find the relevant quantities, right? So relevant quantities sometimes it can mean the relevant degrees of freedom in the system, right? So if you're thinking about a relevant, if you know particular relevant degrees of freedom in your system, all right, then sometimes, well, of course, you need to be careful what you are doing because that's the quantity you like to calculate, right? So it should not get obscured or hidden during your calculation. So you try to calculate that guy. So you need to keep track of that things. Now, what happens normally, for example, if you are familiar with the quantum field theory, or is that you always write your quantum field theory based on some degrees of freedom. So you pick your degrees of freedom, and then you start playing around with those degrees of freedom, right? For example, it can be anything, but that's the important part. The only quantum field theory which you don't actually write the Lagrangian is actually conformal field theory. So the conformal field theory works more like a bootstrap kind of idea. But the other, whenever you write about Lagrangian, you actually already picked your degrees of freedom, and you say that these are the important things for me, right? Now, when you do dualities, then you need to keep track of those things if those are the things that you are interested in. In some cases, there is a recipe how to, after doing all these mappings, how you can come back. And in some cases, if you don't have the recipe, then that's not going to be useful for you, right? You shouldn't do that because you don't know how keep track of those information that you are talking is popping up, right? So it's always about being smart and knowing that knowing that how you can actually, after doing some movement, some changes and stuff, how you can still get what you originally intended to get, right? I don't know. This answers your question, or
yes. Thank you very much.
Yeah.
Adelante, Denis, por favor.
Well, thank you for your talk, Professor Mohammed. I just have a small question about a specific calculation. We were talking about yesterday when we were working about Bayesian integration. I don't know if you can go to the slides.
Yes, let's go back
Please.
here.
Yes, that one. Well, it's just a small question. In the second Bayesian integral that you have defined, where you have the integral of theta d theta equal 1, right? There are
Yes.
people on field theory that usually uses the differential at the beginning of the integral. And well, I have heard that when you commute, for example, the differential with the variable itself, you will gain a minus sign. So instead of one,
Yes.
you will have -1. I don't know if you can say something or if this would change something on Bayesian
Well, the
integral in any
derivative
other
in
different area that you
integrals.
have. Sorry?
Yeah. So, well, let's talk about a bit about the history of this definition. So, why is defined like this, right? So, the reason is defined why it's called integration. So, historically speaking, Grassmann was not the person who actually did anything about this integration. It was mostly even, it wasn't even very, it was a bit earlier. So people, when Dirac and Feynman, they invented the path integral, right? People, they were able to do the path integral for bosonic systems. And it was a question that how we can generalize to fermionic systems. And then people, they came up with this idea. And then Berezin was the person who made the mathematics of these things precise. Now, and why they called it integral? Because of the path integral. It looked exactly like equivalent of the path integral for bosonic system, right? That was invented by Dirac and Feynman. And this was giving the quantities that it looked exactly like that. So that was the reason they started calling this integration. And then regarding your question is, it's possible to show that, if you want to have a consistent way of defining things, the integration and the derivative, they end up to be almost the same thing. So I never do a derivative actually, right? So I like to write it like this, an integration. But some people, they also like to write the derivatives, and the derivatives it's also end up to give the similar results as the integration. I don't know that this actually answers your question or not.
Yes, I was talking about that. Well, thank you, Professor. And well, again, thank you for
Yeah,
your nice talk.
you are welcome.
Well, we have a question here on the chat, so I'm
Yeah.
gonna read it. Luis Yapu is asking, when is the duality step useful or necessary before approximating by steepest descent?
Yes. So a very good question. So the reason is that you can go from this here, from this part to this part without doing this. Well, actually, you can go from here also here and then jump this part, right? So the reason that this jump, it's actually, you can do this, no problem. But the point is, your approximation sometimes, actually, in many cases, actually the cases that we studied, we learned that this actually gives you a much better results rather than doing this, going from here to this and then doing this steepest descent. And what is the reason? The reason is that, all of these steepest descent approximations in zero order is almost like a mean field, what we call mean field theory. I don't know that you're familiar with that or not. Now, the mean field is normally works, we say that when everything is kind of connected to everything else in some sort of a non-local way. Because the mean field works better, as I was telling you, for example, if everybody was coupled to everybody else, somebody else asked the question, right? Then I said that that's exactly solvable. It's an easy problem, right? But if everybody is not connected to everybody, then the problem actually gets more complicated. Now, what this duality part does is that it makes the original problem, which was not like a non-local or everything is connected to everything else. This guy actually sometimes make that kind of mapping. So here, when you do this, then you end up with a problem which looks like most of the things are connected. Of course, it's not exact, but since the interactions or the couplings, they end up to be more non-local, then when you do the steepest descent approximation, you actually end up to get a much better results than doing directly from here to here, and then this one. So this is actually probably the most important part of this program, because it's not like people, they didn't know already this and then this and this. This actually, the central part is actually what is the most the newest part of this program that I'm telling you. And the reason is, intuitively, as I told you, is that it gives you more opportunity to do to get a better approximation. Like, imagine that you go from here to here, and here you need to do 10 terms of your approximation. This guy, when you add this dual fermionic in the middle, this 10 terms of approximation can be reached already by just the zero term, the one term in the approximation. I hope that I'm explaining it properly. So this makes the convergence of the results much faster than jumping this step. Does this answer your question? Okay.
Well, are there other questions, maybe? Well, I think there are no more questions. So thank you, Dr. Mohammed. It's a pleasure to have you here. It's of course an interesting talk. I think this is too interesting, and it's an opportunity for people to see this kind of work. So, I hope that we will hear from you in the future. So, thank you very much. And,
thanks for the invitation.
Yeah, thank you also, Eddie, which he was the contact that we used to arrive to you. So, thank you, Eddie. And thanks to the participation of everyone. We will be in contact. We have the classes tomorrow for all the assistants, so we will continue tomorrow with all the other courses. So thank you, Mohammed. Thank you to everyone, and see you soon.
Thanks for the invitation and everything, and have a nice evening.